When we last left off, we were talking about the amino transferases and how amino transferases have three distinct reactions that they catalyze, and one of which is what I would consider the main one in this box here, which is the amino transferase. And we're going to break it down to each one in just a moment. I do want you to know the mechanisms for this. Remember, it takes as a cofactor pyridoxal phosphate, PLP. That PLP is covalently, that's true for all three of these mechanisms. That PLP is covalently attached on the enzyme on the end of a lysine there, okay, forming that shift base, which is just a nitrogen-carbon double bond, special imine right there. Okay, so it does a amino transferase reaction. Then, and remember this is kind of odd the way they have it done, the second possibility is racemization, which is just a fancy term when we say something is being racemized. What's happening there? We're just switching stereoisomers. We're not changing anything with the amino acid at all. You're literally just going to take the amino group from one side of the chiral carbon and put it on the other side of the same chiral carbon. Okay, so go from D to L or L to D. And then the third one, which is the one that's the more distant related of those, is actually decarboxylation. And so PLP is involved in a couple of different types of reactions. One is just moving the amino groups around, and second is it can be used for decarboxylation reactions. And now we're going to just break this down to each of the individual ones. Let me make it a little smaller. So the way that this works, and this is a very important mechanism. Remember, one thing is every single amino transferase will always have two substrates and will make two products. Because it's a ping pong reaction, because literally you're going to take the amino group from one thing and add it to the keto acid of something else. So in doing that, you're going to make the keto acid of the original amino acid, and you're going to make the amino acid, the others, keto acid. So many times they're going to show this, the way that this is shown is it looks like it's just 4 steps, and it is 4 steps, but then to get it back, to get your enzyme back, you have to go backwards. So it's fully reversible. And you started off with this pyridoxal phosphate, and then whatever amino acid that we were going to be, in this instance here, we're going to actually be deaminating it. Okay, removing the amino group from it. Okay, it just, the way that what happens here, and that's not shown, which I really wish that they would have shown it, is the fact that this nitrogen is just going to take the place of the nitrogen of the imine. Because since it's a nitrogen, it can attack up to 2 times. So it's going to attack once to pop off one bond, and attack the second time to pop off that second bond. So what's not shown here is the enzyme is still there. This is all taking place inside the active. Oh, that's really skinny. Let's make it ample, more ample maybe, inside the active site of the enzyme. So the enzyme is still here. It's just that the lysine is now a free lysine. So that's the lysine that was right there. Okay, because essentially it was attacked by this amino group here in order to just swap the nitrogen spots. So if you notice, we had a carbon-nitrogen double bond here, that imine. We have another imine. It's just the amino acids nitrogen is that imine now. They just didn't show that because unfortunately a lot of times in biochemistry they skip steps. You know, in organic chemistry, I always tell you, don't skip steps. Yeah, they skip steps. So
that other NH3 group, does that leave as like ammonia or something?
So no, what left is this N. This N is now right here.
Oh,
that's the lysine.
Attached to the lysine.
It's still, yeah, that's still the lysine of the enzyme.
Okay.
It's there waiting to be used again.
Okay, and then that enzyme you said was PLP?
No, PLP is the cofactor. That's this part. This enzyme's amino transferase.
Oh.
Mm-hmm. And so then there's a base, just a general base on the enzyme. So this could be something like a carboxylic acid, like it could be almost any of those, like a aspartate It could be, glutamate. It could be anything that can take a hydrogen, a histidine, something like that is going to come, and it takes the hydrogen off of the C alpha of that amino acid. Boom. Of course, the electrons have to go somewhere, and so they're going to go down here. This is why this is called an electron sink, because it goes kind of like it's going down a drain. Okay, so these electrons flow towards this nitrogen. Something's got to break or give, and what it does is the double bond just flips down. Something's got to break or give, so this double bond goes here, and that double bond goes there. And this is the important part here. This is called a quinonoid intermediate, because it looks a lot like a quinone. So we're going to see that over again and multiple times. These quinone or quinonoid type looks, or intermediates, a lot of times they look something like this. Because then they can also be converted into something like a benzene ring with alcohols and things like that. Which we kind of cover that, well, we cover that in organic chemistry too.
So you're saying it looks like
it looks and behaves a lot, because anytime that we have that, if you remember from organic chemistry too, anytime you've got a benzene ring with the alcohol directly hanging off of it, you can play around with those double bonds. So that's why those are called, it's called quinone, or anything that kind of looks like it's called quinonoid. So that's where we're up here, this quinonoid intermediate. Then you just get the reverse. So this bond here that became lone pair electrons goes back to reform the double bond. Something's got to break or give. So it's going to reform its double bond, and then this double bond goes and it just takes a hydrogen from a general acid. Which in biochemistry, a lot of times they'll just, if it's a water, if it's a general acid, they'll just put an H there. It's like their fudge factor, I guess you can say, almost. Okay, so we still have what had been that amino acid is still covalently attached right here. Because that's why that one color is the C alpha from whatever we started off back at this point. Okay, then what's not shown, which I really wish they would have shown, what I'm going to do is let me go back here, and I will draw it out. Oh, whoops, I didn't bring it up. That helped. I'll draw out the way that the water works. At one time, so I'm going to do it some time. Chemistry 2. So I don't want to draw the quinone incorrectly. Okay, that's the way I can see it. So I'm going to draw that last step. Draw it out. So we have that C alpha from the original amino acid with whatever the R group is of that amino acid, and it could be anything except for a glutamate. Well, I should take that back, because going backwards it could be a glutamate. Okay, but so it could be any of the R groups. Then we've got the carboxylic acid portion, which I'm just going to draw like this rather than draw it all the way out. You know, that CO2 portion of it. We have the double bond to what is its nitrogen, which is connected to a carbon, and that carbon is double bonded. Oh, I went one step back too far, so actually I'll show you the last two steps. That way you can see a bigger H. Make sure I put the double bonds in correctly. This is not important in the chemistry part. Okay. And they like to show it as a hydrogen here. That's not as important for the chemistry. All right, so then what happens is in the next last step, one I just already went over, was there's this proton. Of course, protons don't do attacking; they're not nucleophile. But one plus about these quinones and quinonoids and things is you can rearrange their. Oh, I'm missing a methyl and alcohol that have absolutely nothing to do with anything. This is a methyl group. This is the alcohol. Okay, alcohol. Yeah. Okay. So what happens are these lone pair electrons go boom, sound effects optional. Something's got to break or give, and what happens is this double bond moves up here. Something's got to break or give, and this double bond here is actually going to swing up. Okay? And, oh, I'm missing a carbon. I'm sorry. How did I do that? I completely do it wrong. I completely apologize. I missed the carbon. It's one of the reasons why I shouldn't have drawn it from that end, but let me just do this again. Here we go.
Carbon dioxide being negative at the very top.
Right, that's CO2 minus, because that's a carboxylate. That's just one way to do it. It's not carbon dioxide, it's just an abbreviated way of writing carboxylate. Okay, so let me try this again. C alpha to the carboxylate. Here, if you want me to, I can even draw it out like that, because it's not really doing anything in the amino transferase part. The R group to its nitrogen. And technically right now, this is a double bond. 1, 2, 3, 4, yes. I'm making sure I don't accidentally, that had a hydrogen and a plus. And then this is where I made my mistake, is it's one carbon, because I forgot the carbon of the pyridoxal phosphate, which is important. Then it goes down to the benzene ring. Well, technically it's not a benzene ring, so there's nitrogen at the end. Phosphate. CH3. Okay, let me make sure I didn't skip anything. Okay, now put the double bonds in for the next to last step. We have a double bond there, and a double bond there. 1, 2, 3. Yes. Okay. See, this is the carbon that I put this carbon at that position instead, but I was missing a linking carbon. Again, we're going to start actually with these lone pair electrons of what have been the electron sink. They're still going to go up to form the new double bond to its neighboring carbon. Something's got to break or give. So this then comes, it smacks to the carbon that if this was a clock, it would be at the 12 o'clock position. Something, again, has to break or give. And it's going to be that double bond between the two carbons. And this is where the hydrogen that comes from either the solvent, which, we're water-based, so that could be water, or maybe it's a generic acid. Okay, it's not shown right here. And what happens is this is going to swing out to take that hydrogen. This is reversible. Okay, so now I'm going to draw the benzene ring, which we're actually finished with the benzene ring at this point. That's a nitrogen. There's only one bond between the benzene ring, between the aromatic ring and the carbon. But now that carbon's going to have 2 hydrogens on it. Make sure I didn't overlook something. The nitrogen I'm going to go ahead and abbreviate it now as a CO2 minus, that way it's just easier to write out. We have that. Okay. This right here is supposed to be a plus. It just didn't come out very nicely. Now, what your book doesn't show you is the hydrolysis portion of this. And so now what's going to happen is a water molecule comes in. And there's lots of water around. I wanted to do a different color. A water molecule comes in. Of course, water can be a nucleophile. We've only got a couple of places where this can attack. What's one of the places that this could attack? What's one location? So, right, if it attacked the nitrogen, because a lot of people say, oh, either this nitrogen or that nitrogen. If it attacks one of those nitrogens, you're going to form a new bond, and that nitrogen is going to have a lot of bonds around it, okay? And that oxygen is going to be positively charged. The other one is, if you think back to organic chemistry 2, is the carbon of the, even though the nitrogen is positively charged, it's more electronegative than the carbon of the imine. So it's actually going to come in and attack that carbon. And so that's where we have, boom, something has to break or give, and what it does is one of the bonds moves down to that nitrogen. Yes, I said it right for a second. And that's why they don't show all of this. They just show it as one step, and they do that a lot with biochemistry. But I'm going to show you that in-between, what that in-between would look like. So once again, it's going to be, if you don't mind, I'm going to call all of this, this ring, just because I don't want to have to draw it. I mean, it's completely done with in this instance. I'm just going to call it, use the phi symbol, so that way it's a lot easier to draw. Okay, so we have the phi, and it's attached to the carbon. I'm trying to keep the color scheme the same. We have the nitrogen, hydrogen, pair of electrons. Only one bond now between the carbon. Oops, that's supposed to be a CO2. What's the R group? And the water. Now, one thing I'm going to show you is I'm going to describe the head in the water as an OH, because the extra hydrogen can go to multiple places. One is it can go to this nitrogen. That nitrogen is perfectly fine. Second is it could be the replacement for the hydrogen that was picked up before. So that's why in biochemistry a lot of times they don't show it. Pops on and off all the time. It's one that's solvent exchanged. Then the only thing that's left is, let me use a different color, is you just get a repeat. That oxygen, the lone pair of electrons on the oxygen come and smack that carbon once again.
Where did that double bond go?
It became the lone pair of electrons. Or it could also be a bond to the hydrogen that Ms. Deere sees off of the water. Okay. But the second half of that one step that they don't show you is the fact that the lone pair of electrons of the oxygen just attack again. So what happens is, since water has two lone pair electrons, that water can attack twice, and it's going to just knock off the nitrogen that's got two double bonds on it. And so something's got to break or give, and what breaks or gives is the fact that this is going to go towards the nitrogen. And I'm not going to, just because there's a lot of, it would make it kind of messy, this nitrogen can use those two extra electrons to come and to take off this hydrogen up here. Because if we don't, that oxygen's going to be positively charged and the nitrogen's going to be negatively charged. So like the moment that nitrogen gets that double bond, it's going to take that hydrogen. Or a water's going to take the hydrogen and don't it back, but it happens instantly. And so, in the end, we get all that benzene stuff back. We have the carbon with the hydrogen. But now, In fact, I'll even put it in that, what is it, that blue color? That way you can see. Okay, or you could even do it as an NH3 plus if you really wanted to. If you wanted to show both of the two blue hydrogens there, that's fine. So that's one product, but that one's still attached to the PLP. And then the other product is what had been the amino acid is now the alpha keto acid. Okay, here, let me hit. So now that this is what we formed, I don't know if it'll let me erase. Oh, it didn't. It kept the pictures, unfortunately. But this is what we formed right here. We have our alpha keto acid and we have this nitrogen that's on the end. But we've got to get that lysine back connected to it. And so it's literally just the reverse here. To get the enzyme back on there. So whatever the second alpha keto acid was, which let's say, for example, it would be alpha keto glutarate. For example, for alanine amino transferase, we started off here with an alanine and we got pyruvate. But we've got to get our enzyme back. And the way we get our enzyme back is an alpha keto glutarate now comes in and it does the exact reverse. So that way you get your enzyme and you get glutamate. It's the exact reverse. So what happens is the alpha keto glutarate comes, this nitrogen attacks it twice. Okay, so now it looks like this. And then you just do the... Yes, that's why we started off with an alanine. We made a pyruvate. It will always be alpha keto glutarate that comes in, and you make a glutamate. Okay. Or the opposite of that is we start with a glutamate to make the alpha keto glutarate, and then, for example, pyruvate comes in, and you make alanine. But every single that's the important thing. Every single amino transferase, what it does is it's going to have two substrates and two products. One substrate is always going to be an alpha keto acid, and then one substrate will be an amino acid. So let me see. I'm going to call it alpha keto acid X. Okay, we'll go on to make the alpha amino acid of whatever X is. X. However, in order to do that, you have to have something that donated that nitrogen. That's going to be glutamate, going to make alpha keto glutarate. That's why it's reversible. That's why amino transferases, you can't get rid of that nitrogen from a glutamate using amino transferase because every single amino transferase uses glutamate. So glutamate has to have something special. Okay, whoops. I'm going to go more quickly over the next two because I don't want to say that they're not as important, but they're not as often seen for this class. The first step is exactly the same. So we have a base that comes in, you form your quinonoid intermediate. Then, once again, what happens here is instead of we reformed what looks like a benzene ring, the aromatic ring, but instead of this bond coming and taking the hydrogen, it actually flips up to the nitrogen, and it's this carbon that takes the hydrogen. Then, it's literally just the enzyme comes in and smacks this carbon and pops off the same amino acid. You don't change the amino acid on there. You just go from L to D or D to L. So that's why it's a lot easier than the first one. And then the third method, oh, yeah, I made that little note because in the figure that came with the book from the 2008 edition, one of the carbons was missing a hydrogen. The third method is a little bit more tricky. Okay, so once again, we start off with the same thing that we had before with our amino acid. The nitrogen of the amino acid is going to replace the nitrogen of the enzyme, just like we had before. But for decarboxylation reaction, instead of it starting, down here somewhere for things to move around, it's the electrons of the carboxylate is going to come and smack into the carbon. Something's going to break or give. It's okay. Something's going to break or give, and it's that carbon-carbon bond, single bond. So whenever that happens, they don't show it very well, but whenever that happens, this leaves as a CO2. Okay, so that's why it looks like this. Then at this point in time, it's actually very similar to what we saw in the first reaction, in the fact that you go to reform that aromatic ring, this comes up, smacks the nitrogen, makes the double bond, so that's why it gets the hydrogen. Then the enzyme nitrogen just comes and smacks the carbon. Whoops, smacked the wrong carbon. Smacks the carbon twice, and it pops off what had been your amino acid is now an amine. So this is one way that our body can go. We're going to actually see this a lot in chapter 23 when PLP does decarboxylation reactions. Because an example of this, like one that has medical implications, is histidine. Oops, I can't spell histidine. What is histidine if it loses its carboxylic acid? Technically, it is reversible. It does require PLP. What does histidine become if it becomes an amine? Histamine. And we'll see that over and over and over again. That this, by the way, is an aromatic decarboxylase. That's the enzyme that uses PLP. Okay. All right. So now we did that. What happens to glutamate? Because this is the problem. Remember, we're trying to, if you remember, the overall goal of this is we've trying to get all the energy we possibly can from our amino acids now. And so the way you have to get rid of nitrogen, and we can use these amino transferases to start the ball rolling to get rid of nitrogen for all of the backbone, for all of the amino acids except for glutamate. Okay? Because glutamate cannot be used by the normal amino transferases, and I'll just give this. The answer is because what amino acid can accept a nitrogen? You would just make the same amino acid over again. And so it'd be a futile cycle. So we have to have some other type of way. And so this is just a fancy way of saying that the glutamate has got to go to the mitochondria of a liver cell in order to go what's called the oxidative deamination, which really sounds, be careful when you say it. Sounds almost like a theology class. Oxidative deamination. Hellfire kind of thing. Okay. Now we're getting back to kinds of things that we've seen before. Okay. So this reaction's pretty simple. This is the enzyme that does it. Okay. We have glutamate. It forms an imine intermediate, but then it kicks it off with the water, and so now we have alpha-ketoglutarate. So now the alpha-ketoglutarate can go on and do citric acid. Oh, whoops, gave it away. You can go on and do the citric acid cycle, right, to make more energy. And we can now get rid of that nitrogen. The nitrogen, well, if you're a fish, it can be excreted. But of course, we're going to use it in the urea cycle in order to get rid of the nitrogen. Okay. So what class or classes of enzymes can do this? Dehydrogenase. And so if you were to name this one, what would you name it? This is glutamate dehydrogenase. See? We've learned a lot this semester already. This is glutamate dehydrogenase. Okay. And by the way, it's the only known enzyme that can take either NAD plus or NADPH, because all the others take one or the other.
What is the P?
The what?
The P.
The phosphate. It's phosphorylated in one of the positions. Whereas there are certain enzymes that we've talked about in the past, we've only talked about one or two, that have to have NADP to NADPH. This is the only one that'll take either one. It doesn't matter. But yeah, in case you don't. Oh, and then it should also make sense, like what activates it and what inhibits it and stuff like that. Like, what does it make sense that this enzyme would be activated if ADP concentrations get too high? Where did the ADP come from? ATP. That means we've been breaking down ATP. And this one's actually inhibited by GTP. And remember, GTP is a lot like ATP. So if you have a lot of GTP around, that means you've got a lot of energy already. Okay. I'm kind of going to go quickly over this one because whenever it becomes available, you can read it on your own. Now we have to try to think, how do you get rid of the nitrogen itself? We've taken it off the backbone, but we've got to get rid of it. And so it depends on a couple of things. One, it depends upon what tissue it's in. So we have the skeletal muscle and we have the other tissues. If it's intracellular, okay, what does intracellular mean? Within that same cell versus intercellular. If it's intracellular, you can just use glutamate. Just like, well, I mean, that's one way to get it from one part of the cell to the other part. But we don't use glutamate inside through the bloodstream. So any free ammonia would be really bad, and we'll get to that in a moment. Like, you don't just have ammonia running through your veins. Okay, so free ammonia would be really bad. So any free ammonia actually uses glutamine. Okay, so it's not glutamate, it's glutamine. Okay, skeletal muscles use alanine instead of glutamine. Does anyone remember, like, what happens in skeletal muscles? Like, what do we undergo with, well...
Like the anaerobic?
Right, because under anaerobic, and so we get a lot of pyruvate and lactate, stuff like that. So that's why it makes sense. They have a lot more alanine around. That's actually, I jumped a gun. I went out of order. Oops. Okay. All right. But remember, inside the same cell is glutamate, no big deal. We can just use amino transferases. But once you want to go from one organ to another organ in the bloodstream, you're going to use either glutamine or alanine. Alanine is for muscles. Everything else is going to use glutamine. Glutamine is very important. It's one of the reasons why it's in such high concentrations in your blood. Alanine and glutamine are, because they're transferring nitrogens from tissues to tissues. Okay, first, glutamine is non-toxic. That's important. If you're going to have it in your blood, you don't want it to kill you. It's high concentration because of the fact that it's used to shuttle nitrogens around. And what we'll find out later on is glutamine itself can be used for multiple biosynthetic reactions. One of which, I mean, we can utilize glutamine to make, for example, glutamate, which we already talked about, but things like that. So we have glutamate. The first step uses an ATP. The only thing that's different is the phosphate gets put on the very, very end. Not the backbone, the very end. But what class or classes of enzymes can do this? So we went from glutamate to make what's called gamma, because that's the carbon, alpha, beta, delta, gamma. That's why it's called gamma. Gamma glutamyl phosphate. What classes? We only had certain classes of enzymes that actually utilize ATP. There's kinases, and then there are synthetases. The only thing, this is a synthetase. Okay? This is a synthetase. So that's why I wanted to put down the fact that it's the same enzyme. It's a two-step process. Okay? And so if you're going to name this one, what would you name it? That would be one possibility, but it's the same enzyme that does two steps. So what's the name of this compound right here? That's glutamine. See, it's right there. So it's glutamine synthetase. Whoops. Bring this back. It ultimately makes glutamine, right. Okay, where? Right, so then we go from glutamine to glutamate. So, we start with the glutamate, you're going to end up with glutamate, but it's only in the liver mitochondria. Okay, which makes sense, because what's one of the functions of the liver? In this instance here, it's to get rid of nitrogen. So that's why only the mitochondria of the liver will need that last enzyme, because otherwise, if it was in your brain would be getting rid of its own nitrogen that it may still need. Okay, so your brain sends it in the form of glutamine down to your liver, which your liver hepatocyte now can go ahead and take glutamine, okay, and remove this nitrogen. What class? Oh, well, actually, this one, I was going to say, it's a deaminase, but this one's got a special name. And the special name for this one's called glutaminase. I love that name. It tells you exactly what it does. Okay. So it's glutaminase. And that's right where I'm going to pick up for the next.